Okay, so what we're going to look at here is how the slag affects the reaction of Portland cement and how the Portland cement affects the reaction of slag. And this has been quite difficult to do up until this study here. So you'll see thousands and thousands of papers in the literature on Portland cement slag blends which plot the development of strength and lots of other things with time. But what these papers can't do was to say how much of that comes from reaction of the slag or the other supplementary cementitious material and how much from the Portland cement. And this is really where we want to have a better basis for understanding, because if you want to use a wider range of supplementary cementitious materials, you need to have a more precise idea of how the reaction of these different materials is going to contribute to the overall blend. Now, what we have that's very important with all additions to concrete, we have a lot of effects that are called a filler effect. Now, a filler effect means this is an effect brought about purely by the physical presence of this addition. So in these results here, what we've done, we've taken pure Portland cement and we've blended it with quartz. Quartz is pretty unreactive. We may have a very, very small amount of material on the surface that reacts, but in general, you can assume it's unreactive material. So in terms of having a baseline, we want to see what happens when you just put in a purely inert material into your Portland cement. Because only when we've got that baseline can we better understand the additional effects that are brought by any reaction of this supplementary cementitious material. And what we see here, these are results from calorimeter output. So this is the heat flow, this is the rate of heat evolution, and this is the cumulative heat evolution. So this is like the rate of reaction, this is like the overall amount of reaction. And in terms of the rate of reaction, you can see that we've got very, very little effect on this first slope here, this first bit of reaction of the Portland cement, but that this reaction seems to go on a bit longer after the peak. And we're pretty sure that that prolongation of the reaction, the time extended, is because there's actually more space. Okay, now that's a bit difficult to understand because we've mixed all of these with the same water to total solids volume. But the point is that in one case, everything's reacting, so everything's producing additional volume that's filling up space. In the second case with the quartz is not reacting, so this means proportionately there's more space available for the cement to fill up. Okay? And because of that, we see this extension of the reaction longer after the peak, and then slightly higher reaction thereafter. And in terms of the cumulative reaction, we can see this translates into quite a bit of extra hydration of the cement. So you can get to higher degrees of reaction of the cement purely by the fact you've got this inert material which is giving it more space to react. And typically it amounts to about 5%. Now, if you've got a very, very fine particle, like if you've got this silica fume, which has this size of about 1/10 of a micron, we know silica fume is reactive, but even though it's quite reactive, there's almost minimal reaction in the first day. In the first day, the action of silica fume is mainly to greatly enhance the reaction of the cement. And you see, it enhances the reaction of cement, but it also changes this slope here. This slope here is to do with the nucleation and growth of hydrates. And because we've got these very small silica fume particles, they give extra surface for nucleation, and they allow more hydrates to form. This is also why they produce materials which are higher strength, because there's a more even distribution of the hydrates throughout space. So these are two filler effects, and you see these two filler effects can really be very important, and that's before you get any reaction of the addition itself. So just to summarize this, we see that we can get effects from the filler effect, but we actually seem to have larger effects on the calcium aluminate, which I'll show you about in the next couple of slides. So the effect we have on the aluminate reaction, we can see again in terms of the slag. And here what we have in blue, we have the original Portland cement. And in grey, we have an addition of quartz, which has a very similar shape to the blue curve, but you see again the reaction extends longer beyond the peak and ends up being slightly higher. This is just a pure filler effect. Now we put in the slag, and we see that the effect on the silicate reaction is more or less the same as a filler effect, but there's a much more pronounced peak here. And if you remember well enough from before lunch, that second peak there was a second reaction of the aluminate phases. And we did a lot of work, which I'm not going to go into all the details. We did a lot of work to really say, what is really happening here? Because many people have said this is a first reaction of the slag. But we thought this may not be the case, because here, sorry, that's just to say this question, is this just a filler effect, or is it a reaction of the slag itself? Now, the reason we thought it probably might not be a reaction of the slag is because we had previously these results, and these results were done to really see what would be the effect of a filler in terms of X-ray diffraction. In X-ray diffraction, you often want to have a reference material, and it's often thought to be preferable to blend that reference material with your material of study. And here we have two typical references for X-ray diffraction: corundum, which is a kind of alumina, and rutile, which is titanium dioxide. And both of these two are thought to have minimal reactivity. Certainly rutile, titanium dioxide, is really quite an inert material. And despite the fact these are inert, despite the fact they're not reacting themselves, you see they produce the same effect on this second aluminate reaction. It goes from being quite a broad peak to quite a sharp peak. And that's very similar to the effect produced by the slag. So we then did a much more detailed study. We did a kind of deconvolution of these curves to subtract the contribution of the aluminates from the contribution of the silicates. And when we did this, we saw that the amount of C3A reaction in that second peak was roughly the same whether you had slag there or not. So there's quite a big error in these figures, but within the accuracy of the calculation, we can see within each group here, each group is for a different cement. The amount that reacts in that second peak is very similar. So the slag does not change the amount of reaction, but changes very much the nature of that reaction. You see that this peak has become very sharp, this down curve is much steeper, and this is almost certainly due to the modification of the nucleation of the aluminate hydrates. We don't know all the precise factors of this, and that's one of the subjects of the thesis of Elise. If we then go back and look at longer time, so this is what happens in the first, we've been looking at what happens in the first day. Now we want to look to longer times, and we can look in turn at the effect of the slag on the reaction of the main clinker phases. This, for example, is C3A. The accuracy of these measurements, because we're dealing with quite small amounts, is quite low because we have to consider an error of plus or minus 1. But within the error, we probably don't see any major effect in the long term on the reaction of alumina. We see a very slight effect. We see a very slight retardation here on the reaction of the silicates. But when we measure over longer scales, we see that the reaction of the silicate phases is really quite similar. What is very different is what happens to the B-light content. Now, you may remember that I commented earlier that the B-light didn't seem to react, and hardly seemed to react in the first 10 days. So you see this blue curve, very little reaction within the first 10 days. And now, when we've got the slag in the blends, we can see this period in which B light doesn't react extends to much longer times. So for this slag 1, we get hardly any reaction for about 100 days, and for this other one, we get hardly any reaction for about a year. And this underlines the fact that it can be quite important, the composition of the cement you blend with your material, because if you want to get a good hydration, a good space filling, it's obviously much better to use a cement with a higher content of C3S rather than C2S. On the contrary to that, if we look at the ferrite phase, you may remember that the ferrite phase was reacting up to about 80%, and now the ferrite phase seems to be much better reacted in the presence of slag, so that we really can't see any trace of the ferrite peak. This is the ferrite peak, and you see here by about, certainly by 90 days, this has completely disappeared. And this is the case in terms of all the different cements. So just to summarize this, over the longer term, there's comparatively little influence on the hydration of C3S and C3A. We've got an enhancement of the ferrite reaction and a retardation of the C2S. So summarizing, this means that the slag itself can have quite a significant impact on the Portland cement. So the second thing we want to look at, we now want to look at how we can measure the degree of reaction of slag itself. And here we made a very detailed study. I'm not going to go into it in all the detail because it's really quite long, but we studied 5 different techniques: selective dissolution, differential scanning calorimetry, image analysis, calorimetry, and chemical shrinkage. Before this study, the main method which had been used was selective dissolution. And the idea of selective dissolution is you have chemical compounds, you mix them up with your hydrated material, and what they're supposed to do is dissolve away everything apart from the slag. Now, when we look at this residue that forms, we can see that's not true, because we can see these slag grains here, but you can also see there's cement grains, there's various hydrate products, and everything else. So this selective dissolution technique doesn't work perfectly, which makes it a very difficult technique to really accurately quantify the amount of slag reaction. Now, you can vary different things, the amount you grind it, the time you leave with the solvent and everything like that. All of these things may change your results, but it makes it a technique that is almost impossible to get reproducibility from one laboratory to another. The second idea, which is also to be found in the literature, was to use this differential scanning calorimetry. And this differential scanning calorimetry, you find that you get this peak here at about 900 to 1,000 degrees, which occurs when the glass phases in the slag recrystallize. So that's the basic idea. You can see this peak here, but you can see also this peak is superimposed on a very steep background, which made it, in practice, almost impossible to get a good quantitative estimation of the amount of slag by this method. So then we looked at an image analysis method. You've seen in the images how we can pick out quite easily the slag grains, and this means we can automate this process by image analysis. The problem we had is that the gray level of these slag grains is very similar to that of calcium hydroxide. So in practice, what we had to do was to use a combination of these kind of images here alongside chemical information, namely the amount of magnesium, which we know is only present in the slag and not in other cement hydrates, and this allowed us to have a good quantitative measure of the amount of slag reaction. And the final methods, which I think are some of the most promising for the future, are to use calorimetry and or chemical shrinkage, which are both continuous measurements. With both measure, you just take one sample and you have a continuous recording over time. And we can see here that we have, first of all, the filler effect I already explained, and then above and beyond the filler effect, an extra heat here, which comes directly from the reaction of the slag. And by subtracting the grey filler reaction from these purple and green reactions, you can get an indication of the amount of reaction of slag. So that's very nice. It's a continuous method. The point is here we have to calibrate it, because here we have a heat evolved per gram of slag, but we don't know what heat should be associated with the reaction of slag. And so we can cross-check between the image analysis measurement and the calorimetry measurement, or the chemical shrinkage measurement, to see that in more detail. And these are, I think, are very promising techniques which we'll continue to study in the future. So that was just to show you what works and what doesn't work. And the big advantage of these techniques is that, of course, image analysis, you need to be able to see the slag particles. That works fine with slag. We've got a material which is very homogeneous, very reproducible. But if we want to study other kind of supplementary cementitious materials like fly ash, calcined clay, silica fume, it's really much more difficult. People have done it for fly ash, but the level of reproducibility is a little bit questionable. What is the big advantage of these continuous techniques is that this methodology works for all supplementary additions. And that just compares the different methods in terms of time and effort you need to do the measurements. So we're running a bit ahead of schedule, but I'm sure you're pleased with that because it's been a long day for all of us. I just want to finish with a short point on mechanical properties, and this was one of the questions that Mo asked earlier. This shows the development of strength for these slag blends, and this is similar to many, many results you can find in the literature. You see that at 1 day, the strength of the slag blends is basically the same as the blends with filler, i.e. at 1 day the slag is not contributing anything to the strength, and the contribution from the slag increases over time, so that by the time you get to about 28 days, the Portland cement blend and the slag blends have roughly the same strength. Now, what was particularly interesting in this case was we had two different slags, and we see that in terms of strength, the contribution from this slag, the purple one here, slag 1, was quite a bit more than this slag 8. This was, in fact, the reverse of what was happening in terms of hydration. You can maybe see here that the green one is actually reacting more and reacting faster than the purple one. And this really then sort of highlights the complexity of what I was trying to say earlier in response to the question, that the contribution to strength is in fact the opposite to the contribution in terms of degree of reaction, which, you know, highlights how much we don't know between what links the phases formed to things like strength. So I'm going to stop there. I know we're running quite a bit ahead of time, but I think that's okay. Thanks to all the people who contributed to this study. I think we'll take a break now, but we'll start again at 3:45. So it gives you a 35-minute break, and we'll start at 3:45.